ACSKB. We are implementing the ACSKB 2010 starter kit using TL082 op-amps. We are implementing the Dou-Thomas biquad filter here. It's a combination of band pass filter and a low pass filter. So the resultant, we will be getting a sharp low pass curve. In the sense, it allows low frequencies to pass through and cuts off the high frequencies. So the first and the third op-amp we realized the band pass filter using the first and third op-amps. The second op-amp is actually the low pass filter, and we are getting the output across the second op-amp. So we are realizing this in the circuit. The first and the third op-amps, which form the band pass filter, are connected in this IC, and the second op-amp, which is actually the low pass filter, is implemented using this IC. So what we are doing here is we are giving the signal through this resistor, that is over here, to the signal generator, and we are varying the frequency from 90 Hz to 1 kHz. We are giving a peak of 2 volts peak to peak. So as you can observe in the output, at first we can see that the voltage is this is the input voltage, 2 volts peak to peak, and the output voltage. When we keep on increasing the frequency, the phase difference decreases and the output voltage also decreases. I'm varying from 100 Hz to 1 kHz. So as you can see, it keeps on decreasing. So this is the implementation of the Dou-Thomas biquad filter using TL082 op-amps.
Multiplier, wherein the multiplier is actually used to reduce the complexity of an IC. This multiplier has been given 3 control voltages: 1 volt, 5 volt and 8 volt. For 1 volt, which is shown in the multiplier as shown in the multimeter. Therefore, as frequency, we increase the frequency from 100 Hz to 1 kHz. When frequency is kept at 100 Hz, the following waveform is obtained on the CRO. And hence, as it is increased from 100 Hz to 1 kHz, as the frequency increases, the output voltage decreases, and also the phase difference between the input and output also decreases, as obtained on the CRO. Okay. This experiment is therefore for 1 volt. The same experiment procedure has been carried out for control voltage when it is 5 volts and 8 volts. The main difference between 5 volts and 1 volt is that the output voltage, when the control voltage is set for 1 volt, the output voltage doesn't increase to more than 1 volt. In the same way, we are calculating the control voltage for 5 volts, and hence the same procedure is done while changing the frequency from 100 Hz to 1 kHz, and the CRO waveform is obtained as follows. Same way we are doing for control voltage of 8 volts, wherein the 8 volts has been controlled and is obtained on the multimeter. Therefore, from this it is clear that when the control voltage is kept for 8 volts, the output voltage doesn't increase more than 8 volts. It falls always less than 8 volts. And hence, again, when the frequency is increased from 100 Hz to 1 kHz, the waveform is shown as CRO. As a result of which, as the frequency increases, the output voltage decreases, and the phase difference between input and output also decreases, which is shown in degrees.
What the thing was, we were one resistor short. We didn't have one resistor, so instead of putting a resistor up on the breadboard over here, we used this branch over here. In the sense, we were short of 1 kilo ohm resistor, so we took a wire from the U2 P1 port, U2 P2 port, and we connected it over here. So instead of using a resistor on the breadboard, we actually used the resistor which is already been given without connecting the fourth op-amp over here. Now let us compare the Bode plots from the simulated and the hardware implementation. The time when we use the kit without the multiplier, we get a big bandwidth, that is, I'm getting a bandwidth of 180 Hz, and through the hardware implementation I'm getting a bandwidth of 140 Hz. And as we keep on progressing while applying the control voltages, we can observe that the bandwidth decreases and gain curve becomes a lot finer. For example, let us consider the 1 volt graph Bode plot. Here we can see that when I am applying a control voltage of 1 volt, I am getting a simulation of 160 hertz of bandwidth, whereas when I am through the readings of the tabular column which we did implemented using the starter kit, I am getting a bandwidth of 130 hertz. And the phase plot, and another observation we also made was, once we increase the control voltage, the phase margin is in sync with the input voltage. The output voltage is in sync with the input voltage. Similarly, let us move on to 5 volts. Here you can see that the bandwidth decreases. It was 160 hertz before, and now it is just 140 hertz. And through the hardware implementation, I am getting about 112 hertz. And similarly, with 8 volts, I am getting 130 hertz in the simulated and about 110 hertz in the hardware implementation. So basically the function of the multiplier is that you get a smaller bandwidth because of the trimming action of the multiplier. So it is basically you are getting a smaller curve, and that is basically the Thomas Bicquart filter.